Now let's talk about derivatives and the shapes of curves. So we're going to kind of take those critical numbers that we just learned about in the previous video, kind of kick it up a notch. So we said, all right, so we've talked about critical numbers, and what we're going to kind of do is kick them up a notch with learning this first derivative test. But before that, I want to remind us about increasing and decreasing. So we learned when we first learned about derivatives a while back, we talked about how when the first derivative is positive on an interval, then that means that the function is increasing on that interval. If you think about it, if we have like an increasing function, it's going up, well, obviously that is going to have all of the derivatives at each of those points are going to be positive. The slopes of those tangent lines are going to be positive. If the derivative is negative on an interval, then the function is decreasing. So if it's decreasing, if you think about a decreasing function, it's going down, the slopes of all those derivatives are going to be negative. So that's why we say that. So this is going to come into play, this concept, in the first derivative test. So suppose that c is a critical number of a continuous function. If f prime changes from positive to negative, so let's look at what that would look like. So it's positive, which means the function's increasing. Then you get to that critical number, and then it starts decreasing. And again, remember that critical number is either undefined or 0 for the derivative. So you can see here, this has created a local maximum. Now, if we look at it the other way, if the derivative changes from negative, so the function is a decreasing function till you hit c, and then it becomes positive, so all of a sudden the function starts increasing, you can see that that creates a local minimum. And then finally, if the first derivative does not change signs, then we would say that f has neither a local maximum or a minimum value. So let's actually look at some examples using this. Example, using the first derivative test, consider the function f of x equals x cubed minus 3x squared minus 24x plus 10. Use the increasing decreasing test to find the intervals where f is increasing or decreasing. So we'll know that, again, if we look at that increasing decreasing test, we said where the derivative is positive, the function is increasing, and where the derivative is negative, the function is decreasing. So either way, we need to find what the derivative is. So let's find that. So the derivative of this function is going to be 3x squared minus 6x minus 24. So to figure out where this is going to be positive or negative, let's first find those critical points so that we can kind of separate this out into an interval. So if we were doing that, set this equal to 0. So 0 equals 3x squared minus 6x minus 24. Factor that 3 out, and I get x squared minus 2x minus 8. And I can factor that further as 3 times the quantity x minus 4 times x plus 2. So I get that the derivative is going to equal 0 at x equals 4, and it's going to equal 0 at x equals negative 2. So sometimes it helps me if I kind of draw the interval out. So I can see there's going to be 3 intervals to look at. One that goes from negative infinity to negative 2, one that goes from negative 2 to 4, and one that goes to 4 to infinity. So this is where we could have those switches in increasing and decreasing. So what I usually do is create a table, and I let intervals be one of my tables, the test be the other column in there, so it's the test point, and then the sign of the derivative, and then what that means for the behavior of the function. So let's look at this first. So that first interval is from negative infinity to negative 2. So if we choose a test value that's in that interval, we could use negative 3. So when I substitute negative 3 into that first derivative, I'm going to get, and I usually look at it in factored form. So when I substitute negative 3 into that derivative, you get positive 3 times negative 3 minus 4, which is negative 7. And negative 3 plus 2 is negative 1. So 3 times negative, so a positive times a negative, and that's going to end up giving us a positive. So that means if the derivative is positive, the behavior of f at that x value is going to be increasing. Now we'll look at that middle interval from -2 to 4. I think the easiest value is always to look at 0 if it's in your interval. So when I substitute 0 in, you're going to get +3, so a positive number, -4, so a negative number, and then a positive number, a +2. So a positive times a negative times a positive is a negative. So that means the behavior of f, we are decreasing there. And then we'll look at that third interval from 4 to infinity. So let's just choose a test point of 6. You can choose anything in that interval. I'm just randomly picking numbers that I like. So when I put 6 in, got +3, this becomes +2, and that's +8. So a positive times a positive times a positive is a positive. So that means the first derivative is positive, which says that this function is increasing. So now if we wanted to use this first derivative test to find any local maximum and minimum values where those occur at, what I can do is I can look at this and say, okay, so as this x value is approaching -2, my function is going from increasing, I'll do this in green. My function goes from increasing on the left-hand side, then I hit -2, and then it goes to decreasing after I leave -2. So that means there's going to be a local maximum at x equals -2. And then if I look at my other critical point, that critical point of 4, we can see that at x equals 4, the function first value to the left of it, it is decreasing, so it's going down. And then to the right of it, it's increasing, so it's going up. So we can see at 4, we have a local minimum. All right, so let's talk about some things with the concavity test. So what the concavity test tells us is if the second derivative is greater than 0 on an interval AB, then f of x is concave up. And if this looks familiar to you, this is something that we learned back in the first couple weeks of the term. And then if the second derivative of f is less than 0 on an interval, then the function is concave down on that interval. So remember with concavity, concave up kind of looks like a smiley face. Concave down looks like a frowny face. So you can be increasing in concave down, like this piece right here is increasing, but it's concave down. You can also be decreasing in concave up. This piece right here is concave up, but it's a decreasing function as we look at it from left to right. So if I were to go back to that same function that we looked at in the last example, the x cubed minus 3x squared minus 24 plus x plus 10, and we used a concavity test to find where the intervals of f are concave up or concave down. So here's how we can do that. So again, we already found that first derivative. So the first derivative was 3x squared minus 6x minus 24. So if I go to find the second derivative of that, that's going to be 6x minus 6. So if I were to figure out, okay, well, where am I going to have these inflection points? So where is it could potentially change from concave up to concave down? So first what we'll do is we'll find these critical values of the second derivative. So we'll set this equal to 0, and we're going to end up getting that x equals 1. So we only have one possible inflection point. Again, an inflection point is where we change concavity. So we change from being concave up to concave down, or concave down to concave up. So if we were looking at this, let's see. So if I like to draw that number line just because I feel like it helps me. So if I was taking this and separating this into intervals, we'd have the interval from -infinity to 1, and then we'd have an interval from 1 to infinity. So let's see what's happening here. We'll use our test values. We'll do exactly what we did on the last slide. So if I was looking at a test value of this, I'm going to use 0 for that first interval, and we'll figure out what the sign of that second derivative is. And this table of values you are not required to do. I just feel like it's really helpful in being able to kind of organize your thoughts and your information. So I highly recommend doing it if you can. So, okay, so when I plug 0 into the second derivative, so if I go up to this and I look at putting 0 into that, I'm going to get 6 times negative 1, which is a negative number. So the sign of the second derivative is negative, which means that the behavior of the function, so if the second derivative is negative, that means this is going to be concave down. Then if I choose a test value in my second interval, we'll choose 2. You're going to get 6 times positive 1, which is a positive number. So it's going to be concave up. So with that, I can conclude because at 1, I change from being concave down to concave up, I can say that we have an inflection point at x equals 1. So let's talk about concavity again. And I already kind of drew these pictures a little bit on that last slide. But let's bring it in together with first and second derivative sign combinations. And what's going to happen with this is going to really help us be able to get an accurate picture of what a function's graph should look like, knowing if it's concave up, concave down, where you're going to have local maximums and minimums, and all that. So where it's increasing, decreasing. So if I was looking here at increasing and concave up, all right, if we were looking at that, this means so increasing. So so we can see again, this is an increasing function. So that means that first derivative is positive, and that second derivative, if it's concave up, because this is like half of a smiley face, is also positive. Increasing and concave down. So again, you can see this function is increasing. Increasing function has a positive first derivative. And if it's concave down, like a sad face, that second derivative is negative. Decreasing and concave up. So decreasing, that first derivative is negative. And that second derivative, if we're concave up, is going to be positive. And then the last one, if this is a decreasing function, that first derivative is negative. And if it's concave down, that second derivative is also negative. So let's put this all together. Steps for sketching the graph of a function. First, determine the domain of the function. Second, find the critical numbers and the possible inflection points. 3, construct a table with intervals, test points, f prime sign info and f double prime sign info, and the behavior of the function. Plot the points that correspond to the critical numbers and possible inflection points. Use the sign combination from the table to graph f. So knowing these steps now, let's go back and kind of combine everything that we found previously into a single table and then sketch the graph of f. So I put on here exactly what we found for the first derivative and second derivative. So we found that first derivative of x was 3 times the quantity x plus 2 times the quantity x minus 4. The second derivative was 6 times the quantity x minus 1. So we found these critical numbers of the first derivative. So we found this equaled 0 at x equals -2 or x equals 4. So these are our critical points. So these are where we could have some mins and maxes, which we already found. And then we also found the second derivative equaled 0 when x equals 1, which was an inflection point. Okay, so if we're kind of looking at that, let's take those values and let's make an interval that contains all of these values. We've already figured out where something is increasing and where things are concave up and concave down and decreasing. But let's put it all together so I can see how all of the intervals look. So if I take where each of these values, the first derivative and the second derivative equals 0, I'm going to put those into like a number line because that usually helps me kind of be able to visualize. You're going to see that we have 4 different intervals. We have an interval from negative infinity to -2. We have another interval that happens between -2 and 1. We have another interval that happens between 1 and 4. And then we have another interval that happens between 4 and infinity. Oops, let's do that in blue so it all stays the same. Okay, so let's go through and kind of, again, we're combining all of this together. So if we did a test point that's in this interval of -3, so we already have done this test point, but let's just look at it again. So if I looked at the first derivative, so if I put -3 into the first derivative, you get a positive number times -3 plus 2 is -1, so times a negative, and that's -7. So a positive times a negative ends up being a positive number. Now, if we looked at the sign of the second derivative, if I substituted -3 in for x, you're going to get 6 times -4, which is a negative number. So now going back to what we just talked about on that last slide, if the first derivative is positive, that means it is increasing, and the second derivative is negative, that means it's concave down. So I'm just going to draw each of those pieces again so we can just look at what that looks like. So if I have increasing and concave down, that's going to look like this. So that interval is going to be shaped like this. Okay, now let's do a test point between -2 and 1. I'm going to use 0. So if I substitute 0 into the first derivative, you get a positive times a positive times a negative, which is negative. If I insert 0 into the second derivative, I get a negative. So this is going to be, second derivative is negative, so we're concave down. First derivative is negative, so we're decreasing. So it's going to look like this, that shape. From 1 to 4, so let's use the test point of 2. So at x equals 2, this is going to be the sign of the first derivative. So we've got +3, +4 times -2, so that's going to end up being negative. The sign of the second derivative, when I substitute 2 into the second derivative, I get 6 times +1, which is positive. So this is going to be a decreasing function that's concave up, so it's going to be in this shape. And then if I looked at from 4 to infinity, let's choose our test point of 5. That first derivative is going to be positive, and the second derivative is also positive. So the shape of this is going to be an increasing function that's concave up. So it's going to look like that. So now what we're going to do before I insert all of this into a graph is let's look at finding the y values at these certain transitional points. So those transitional points were those critical points and then that inflection point, because those critical points are going to tell us those mins and maxes, and the inflection point is going to end up telling us, just showing us where we need to do a change from concave up to concave down. So again, you can look here and see, oh, okay, this is right where it changes from being concave down to concave up. So that was where those endpoints were 1. So again, we know that inflection point is going to happen at x equals 1. And then our first derivative changes from positive to negative at -2. So that means that you have a local maximum at x equals -2. And then at this endpoint of 1, the first derivative doesn't change sign. So based on that first derivative test, that means there's not a local maximum in there. And then at this endpoint of 4, we change from being decreasing to increasing. So that's going to end up creating a local min at x equals 4. All right, so let's find those y values. So if I take in my function and I substitute -2 into the original function, so you do -2 cubed minus 3 times -2 squared minus 24 times -2 plus 10, you're going to get 38. So that's my maximum value is going to happen at -2, 38. And then we've got our inflection point at x equals 1. So when I substitute 1 into that original function, I end up getting -16. So 1, -16. And then if I substituted in where my local minimum is at f of 4, so again, go to this original function and substitute 4 in for x, you end up getting -70. So 4, -70. Okay. Oh, I lost this guy. All right, so we know that, again, now I can kind of go through and do these graphs. So for the values from negative infinity to 2, so from here up to 2, the shape of the graph is going to look like this. So I'll just draw that shape. Okay. And then I know from 2 to 1, or negative 2 to 1, so this interval from right here, negative 2 to 1, I'm concave down and decreasing. And then at 1, I'm going to change to being concave up and decreasing. And I go down to where negative 4 is, and at x equals negative 4, I have my minimum value. And then as I leave that, so x equals 4, and go towards positive infinity, I'm concave up. So I'm increasing and concave up. And there you go. All right, so let's kind of pull this all together by going through and looking at this function, f of x equals x to the 4th minus 4x cubed. So first, find the intervals where this function is increasing or decreasing. So we know it's going to be increasing where the first derivative is positive and decreasing where the first derivative is negative. So first things first, let's find that first derivative. So the first derivative is 4x cubed minus 12x squared. So we found the first derivative. Let's see the intervals we need to be looking at. So let's find where that first derivative is going to equal 0. So I can go through and factor a 4x squared out of each term, and I'm left with x minus 3. So this is going to equal 0 when x is 0 or when x is 3. So if I put this out, we're going to have x is 0 and x is 3. So if this ends up giving us 1, 2, 3 separate intervals. So if I was creating my table, you're going to have your interval, your test point, the first derivative, sign, and then the behavior. I'm going to run out of space. All right, so first interval is from negative infinity to 0. So test point on there, let's do negative 1. So when I substitute negative 1 into my first derivative, you're going to get negative 1 squared is positive, and then negative 1 minus 3 is negative. So you have a positive number times a negative number, which is going to give us a negative number, which means that the behavior of the function is going to be decreasing there. From 0 to 3, let's use the test point of 1. 4x squared, so 4 times 1 squared is a positive 4. 1 minus 3 is a negative 2, so you have a positive times a negative, which is also negative. So that's going to also be decreasing there. And then we'll look again from 3 to infinity. So from 3 to infinity, let's check 4 as our test point. So 4 times 4 squared is going to give us a positive number, and 4 minus 3 is going to give us also a positive number. So the derivative is going to be positive. So this means this function is going to be increasing there. So if we were looking for where local maximums and minimum values are going to happen, we look at, okay, where does this function change from decreasing to increasing or increasing to decreasing? So where does that first derivative go from negative to positive or positive to negative? So you can see that only is going to happen right here is where we change signs. So that end point of those intervals is at x equals 3. So at x equals 3, the function is decreasing, so it's going down. And then as we're leaving, if we're looking at numbers larger than 3, so the right side of 3, it goes up. It's an increasing piece. So that means we have a local minimum at x equals 3. And we can actually find that value if we wanted to by substituting that into our original function. And we end up getting negative 27. So we know we have a local minimum of negative 27 that happens at x equals 3. All right, so now let's look at the intervals of concavity and the inflection points. So concavity and inflection points happen when we're looking at our second derivative. So to find that second derivative, let's first recall that first derivative. So the first derivative was 4x cubed minus 12x squared. So if I were looking at that second derivative, that's going to end up being 12x squared minus 24x. So let's factor that out at 12x, and we're left with 12x times the quantity x minus 2. So we know that that second derivative is going to end up equaling 0 when x equals 0 or x equals 2. So if I were to create my table, again, I'm going to kind of draw that number line just because it's going to help me visualize what those intervals are going to be. So we've got 1, 2, 3 intervals. All right. So interval, test point, the sign of the second derivative, and then the behavior of the graph. So if I were looking at this, we would have our first interval is from negative infinity to 0. So a good test point is -1. So 12 times -1 is -12. -1 minus 2 is -3. A negative times a negative is a positive. So that means this function is concave up. And then from 0 to 2, if we use a test point there, we can use 1. So 12 times 1 is 12. 1 minus 2 is -1. So a positive times a negative is a negative. So the function is going to be concave down on that interval. And then if I was looking at that last interval from 2 to infinity, great test point is 3. So you're going to get a positive times a positive, which is positive. So the function is going to be concave up there. So this means we can see we're going to have an inflection point that happens here because we change concavity from concave up to concave down at x equals 0. So our inflection points happen at x equals 0. And then it happens again as it changes from negative to positive, so concave down to concave up. On the interval, it happens at x equals 2. So those inflection values happen at each of those points. And then if you were to find those actual points, let's write this down here. So substituting 0 into my original function gives me 0. So I have an inflection point at f of 0 equals 0. And then I have another one when I substitute 2 in at -16. All right, so let's put this all together. So we found before that we had a local minimum at f of 3 equals -27. We also found that we had a inflection points at f of 0 equals 0, and then again at f of 2 equals -16. So let's kind of create this table now that has all of this information in it. So if we were looking at this, we need to have for our intervals, I need to make sure I have all of these x values. So 0, 2, and 3. So this is going to split this into 1, 2, 3, 4 separate intervals. Okay, so we will do interval, test point, the sign of the first derivative, the sign of the second derivative, and then the behavior of the function. All right. So that first interval from -infinity to 0. So before we did that test point, when we did the first derivative test, we used -1. We found that the sign was negative. And in the second derivative test, we found that on this interval, the sign of the second derivative was positive. So that means that this behavior is going to be decreasing and concave up. So if we have concave up, looks like this. Concave down looks like this. So decreasing and concave up is going to be this shape. Okay, next interval from 0 to 2. So we found from 0 to 2 when we were looking at finding the intervals of increasing or decreasing, we actually used a test point of 1, and we found that the first derivative was negative there. When we tested that same test point for the second derivative test, we found that the second derivative was negative. So this is going to be a decreasing function that's concave down. So it's going to look like this. And then from 2 to 3. So a point that we can use there, let's use something like 2.5. So 2.5. So if we were looking at that first derivative, we found that on that interval that this was decreasing. On that second derivative, on this interval, let's see, so at 2.5, if I put that into our second derivative test, we had, this would end up being positive. So this function is going to look like this here. Oops, not like that, like this. And then from 3 to infinity, our first derivative, if we did 4 as a test point, first derivative is positive. From 3 to infinity on our second derivative, that is also going to be positive. So a positive means this is going to be an increasing function that is concave up, so it's going to look like that. All right, so if we were to graph this, let's see, I'm going to have some pretty small numbers on here. Let's go by 4s. And we'll do these guys by 1s. Okay, so we have f of 3, negative 27 is our local minimum value. Oops, we need to make this a little bit further down. So negative 24, negative 28, there we go. All right, so f of 3, negative 27, f of 0, 0, f of 2, negative 16. Okay, so we know the shape as I go from negative infinity to 0, so right here, those values were concave, down and decreasing. Okay, so from 1 to 0 to 2, we are decreasing and concave down, so it's going to look like this. And then at 2, from 2 to 3, we're decreasing and concave up, so it's going to look like this. And then from 3 on, we're increasing concave up, so it's going to look like this. And there you go.